Computer science is built on specific, repeatable solutions. In this series, we walk through 50 of them, from basic data sorting to the neural networks powering modern AI. Our journey starts right here, in the sorting category, with algorithm number 1, bubble sort. It is the inaugural lesson for almost every software engineer on Earth. Yet it is also universally mocked for being terribly inefficient. The logic itself predates its famous meme. Mathematician Edward Harry Friend first described it in a 1956 paper, referring to it simply as a sorting exchange algorithm. The catchy bubble moniker wouldn't appear until 6 years later, when Kenneth Iverson printed it in his 1962 textbook, A Programming Language. From there, its reputation tanked. Computer science pioneer Donald Knuth famously declared that the algorithm had nothing to recommend it, aside from that catchy name. The criticism even reached presidential politics. At a 2008 Google campaign stop, CEO Eric Schmidt asked Barack Obama how to sort 1 million integers. Obama deadpanned that the bubble sort would be the wrong way to go. He was right. But to understand why it fails at scale, you have to understand what it's trying to do. Bring order to chaos using the absolute simplest mathematical rule imaginable, no matter how much processing power it wastes. The mechanic is remarkably basic. You walk down a list of numbers, compare 2 adjacent neighbors, and swap them if the one on the left is larger than the one on the right. You advance to the next pair and do it again. The system repeats these sweeping passes until it can walk through the entire list without needing to swap anything at all. Imagine a heavy, viscous liquid, like a thick syrup, where large pockets of trapped air rise rapidly to the surface. Because of this left-to-right swapping rule, the largest unsorted value in your list acts exactly like one of those air bubbles. It is guaranteed to physically migrate to its final, locked position at the very top by the end of every single pass. This diagram shows exactly how a single pass executes on a 5-element list. Starting at the left, the algorithm compares the 5 and the 1. Since 5 is greater, they swap places. The focus then shifts 1 step to the right. 5 is greater than 4, so they swap. 5 is greater than 2, so they swap again. The 5 cascades down the line. Finally, it compares 5 and 8. 5 is less than 8, so no swap occurs. Pass 1 is complete, and the largest number, the 8, is now permanently locked into its correct top position. To automate this physical action in code, we use 2 nested loops. Looking at the flowchart on the left, you can see the division of labor. The outer loop manages the total number of passes required, while the inner loop handles the actual adjacent comparisons within each pass. But look at the bar chart on the right. Because each pass locks 1 more maximum value at the top, the unsorted region shrinks. Pass 1 requires 4 comparisons, Pass 2 requires 3, and so on, creating a descending stack. Adding up that triangular sum reveals a harsh mathematical reality. As the total number of items in the list grows, the amount of comparative work required grows quadratically. This chart plots input size against total operations, measuring time complexity. Bubble sort operates at O of n squared. Notice the massive gap between that steep orange line and the flatter purple curve, representing algorithms used in modern production systems. Why write it? In the Python implementation, there's a Boolean flag labeled swapped. If a pass completes without swapping data, the program immediately exits. By adding this single logical check, the algorithm's best-case scenario drops down to linear time. If you feed it a list that happens to already be sorted, it confirms the order in one quick sweep and shuts off. In the real world, this weaves bubble sort with strictly limited applications. Use it for tiny lists, nearly sorted data, or on memory-constrained hardware. As outlined in 50 algorithms every programmer should know, this code isn't meant for heavy lifting. Its true value is pedagogical. It is the ultimate gateway tool to teach programmers how to measure efficiency, perfectly exposing the flaws that set up the need for algorithm number 2, insertion sort.